So, we have been looking at this algorithm AO star, and uh, let us now look at a problem graph which is shown on the screen. As you can see, it is an Andor graph. It has a certain set of solved nodes which are shown with double squares, and we assume for the sake of simplicity that the cost of that solution is 0. So, maybe we are solving a problem in mathematics or something like that, and we also have some estimates, some pretty randomly decided estimates of nodes which are not solved essentially. So, you can see values like 6, 8, 6, 7, 3, 4, and 21 has the root has the start has an estimate of 21 essentially. For so, we will look at two attempts to solve this with different edge costs. So, in this first attempt, we assume that the edge cost is 1, which means every edge has a cost 1 associated with it. What does that mean? That if we had looked at this partially refined solution, then the cost of that solution would be 6 plus 7 plus 1 plus 1, which is 15, and so on. So, we will assume that every edge has a cost 1. Later, we will look at a variation where we will see that every edge has a cost 10 essentially. You can see that they have a bearing with whether they are underestimating or overestimating the cost. So, when when edges have cost 1, then you can see that the heuristic values that we have are basically overestimating. So, look at this node for with a value 10, it is saying that the cost of solving that node is value 10 is 10, whereas in practice it has a cost real cost 1, because this is 0 plus 1. So, the cost should be 1. So, you can see that these values are likely to overestimate the values of the actual solution, and we will also see that when you overestimate, you tend to terminate faster. Just like when WA star we saw, if we have a high value of W, it tends to terminate faster than A star, but it does not guarantee you the optimal solution. So, assume every arc has a unit cost associated with it to traverse. Nodes are labeled with heuristic values, as I just said, and solved nodes are represented by double line boxes and have 0 cost associated with them. So, let us start with the first node as before. Whatever we show in this thick black rectangle will be the node that we are about to expand next, and initially of course, it is a start node. So, when we expand the start node, we have two choices given to us, the left choice and the right choice as shown here, and you can see that the right choice is a better choice, and it is also marked by the arrow, and I have also shaded the nodes from where the value at the root comes from. So, the value of the root at this point, it started with 21 as you can see, and after the first expansion of the start node, it has gone down to 11. Where did this 11 come from? This 11 came from the right branch, which is the better branch, which has two nodes with estimated cost of 4 and 5, that is 9, plus the two edges connecting them. So, plus 1 which is 11. The other side, the left branch, as you can see, is 6 plus 7 13 plus 2 which is 15. So, clearly 11 is the better of the two, and this is what the partially refined graph shows at this point. So, it shows that you have to go down the right branch, since it is an AND edge or AND node. You can refine any one of them, 4 or 5. So, let us say that we choose to refine 5 at that stage. So, in the next stage we refine 5, and it turns out that it has only one choice below it, which is that of solving two sub problems. Let us call it A and B. So, that node which had a value of 5 can be solved by solving A and B, and because it has only one choice, that means you know that that node with value 5 is also solved. So, that is why it has got this solved label which is shown by double rectangles here. But you can also see that its cost has come down from 5 to 2, and why is that? Because the cost of solving the two leaf nodes is 0 and 0 and the edge is 1 and 1. So, the total is 2, and the cost of the root has also come down from 11 to 8 consequently, and this of course stays in the as the best path essentially. So, next let us say we refine node 4. So, this node 4 is the one here in this graph on the left hand side where we have refined it. It has got two choices, one is an AND choice on the left and one is an OR choice on the right. And the better choice is the OR choice, because that is 7 plus 1, which is 8. It started with 4, it has gone up to 8, and the left choice would have been 3 plus 4, 7 plus 2, 1 plus 1 would have been 9. So, that is why this is marked as a 7 is marked as the right choice. But overall the right side of the AND OR tree still appears to be the better. So, it still remains here even though the cost has gone up from 8 to 12. So, it started with 21, went down to 11, went down to 8, and now suddenly it has gone up to 12. And why is that? Because this node which had a cost of 4 has gone up by 4 to this one has gone up from 4 to 8 essentially. So, the overall cost of that solution is gone up, but it is still the better option. So, we refine let us say this node 7 as seen here, this thing. Which was this node 7? This node 7 was this one here. We have refined that, and we have found that there are 3 ways of solving that, and their costs are respectively 9, 10 and 10, of which 9 is obviously the best choice. So, its cost has gone up from 7 to 10, as you see, and because of that, the fact that its cost has gone up, this arrow has shifted from the right choice to the left choice. Why? Because the cost of that left choice we had seen earlier was 3 plus 4, 7 plus 1 plus 1, 9. So, that becomes a better choice. So, you can see that at any given stage the best path is marked. From the root you go here, from this node you go here. At some point if you were to shift back to this, then from this node you would go here. So, wherever a node has been refined, the best choice is always marked, whether or not it is part of the prospective solution or not. So, now we have this node with 3 and 4, one of them we have to refine. Let us say that we choose to refine this node 3, which is this node has become 1, and let us say it has one choice which is leads to a solved node. So, its cost has come down from 3 to 1 essentially, which means that the cost of 9 here has gone down to 7 and 13 at the root has gone down to 11. So, the right choice continues to remain the best choice, and this is a characteristic of search when you are overestimating the cost, because the actual cost of partial solutions as they get more refined keeps coming down, because you are overestimating, and once it keeps coming down it always remains the best choice. So, the search never looks at the other side of the search tree. So, in any case, so this is the best choice still marked, and so let us say the next node that you are going to refine is this node with the value 4. The value at the root is the sum of all the values in the shaded rectangles plus 1 for every edge that connects them. So, as you can see 1 plus 4, 5 plus 7, 12 plus 2, 14. So, there is an error there. This is 1 plus 4, 5, 6, 7. So, that is 7. Okay, so this I should not count this. So, this is 7 plus 2, 11. So, this 7 actually comes from its subtree which is here. So, I was doing double counting. So, 7 plus 2 9 plus 2 11. So, that is correct. So, this 4 is the best choice, we go and refine that, and let us say that it has the same solution which has this cost 0, and the algorithm terminates pretty rapidly with this cost, which has now gone down from 11 to 8, and that is because this node which had a value of 4 has come down by 3 points. So, the root has also come down by 3 points from 11 to 8 essentially. So, the algorithm terminates at this stage, and what we see in this thick arrows is the solution, which is a subtree as you can see, or a subgraph as you can see, and it has a cost of 8 essentially. So, next let us take the same graph, problem graph, and assume that every edge has a cost of 10 associated with it, which means for that this heuristic estimates that we have, which are 21 for this and lower values for that, are likely to be underestimates, because at least 10 you are going to add to every node as you refine it further. So, these values are going to be underestimating cost. The graph is still the same, the graph that we are solving is still the same essentially, where these are the heuristic values are still the same, as you can see 6, 8, 3, 4, 5, 7, 9, 10, all of them are underestimates, because the edge below them itself has a cost of 10. All the leaf nodes have a cost of 0. So, it is the same graph, except that we have now made our heuristic function underestimating, and we have done this artificially by inflating the cost of transforming a problem from 1 to 10. So, every edge has a cost of 10, which means that our heuristic values were underestimating values. So, let us see what happens now with this. So, the same first step happens, you refine this root node, the same 4 nodes show up as before, the same right hand side appears to be a better choice. So, 4 plus 5, that is 9, plus 10 plus 10, that makes it 29. So, the first thing to observe is that the cost of the estimated cost of the solution has gone up essentially, which is typically the case when you underestimate cost. And if you remember the A star algorithm, as we went closer to the goal, the f values were actually increasing essentially, and especially in the case when the heuristic function satisfied the monotone condition or the consistency condition, they were provenly known to increase essentially as you go closer to the goal. So, again we let us say choose to refine the same node with the heuristic value 5, and this time what happens, once we refine that node with a value 5, the last time we did that, see this is a cost 0 and this is a cost 0 that we have set for all leaf nodes. Last time this was 1 and this was also 1. So, this 5 actually went down from 5 to 2 essentially, but this time these costs are 10. So, it has gone from 5 to 20, and which is why this right branch has suddenly started looking more expensive. So, what is the cost of the right branch? It is 4 plus 20, which is 24 plus 20 because of this 10 and this 10, and so this will be 24 plus 20, which is 44. Whereas the left branch is 6 plus 7, which is 13 plus 20 is 33, is the better branch essentially. So, you can see that the arrow has, the marker has shifted, it saying no, this looks too expensive, let us go to the other side. And this is also a characteristic of underestimating functions, that this thing that oh somewhere you might get a better option, which is a better choice, and it shifts its attention there. So, we refine this 7 now, and let us say, so this was what was 7 here. So, that is the node that we refined, and let us say that it has an AND choice below it with a cost of 3 plus 4, which is 7, plus 10 plus 10. So, that makes it 27, which means this has become 27, its sibling is 6, which is 33. So, this has become 53 because of this extra 10s that are also sitting there essentially. So, again you see that the best marker is shifted to the right hand side, because now suddenly that appears better, and we go and refine this part, the node 4. So, remember that this is a node we are refining next, and that was the node that we just refined, and it has one child. Uh, it has two options. One is this OR choice leading to a node with cost 7, which is why its estimated cost is 17. So, 7 plus 10 is 17. If it had chosen the left choice, which had also 3 plus 4, which was 7, but it had two edges. So, that would have been 7 plus 20, which would have been 27. So, this is marked as a better choice, and its cost now has gone up to 57, but it is still the better of the two nodes essentially. So, remember that the left choice, so this was 27 plus 6 is 53. One sec, have I made an error here? 53, it was 53. So, it should actually shift to this side, but I will leave that as a small exercise for you to cover there. So, because this is 53, this arrow actually should be here. So, it should go and refine one of these other nodes essentially. But anyway, if you pardon that particular error, let us assume that this 57 is a better choice. We want to see how the algorithm will proceed from here. We came and we refined this node with a value 7, and its value has gone up to 19. Why is that? Because the best choice below that is 9 plus 10 is here, that is 19. So, that is 19. So, this would be 29, which means this 27 is become the best choice. But when you look at 27 plus 20, which is 47 plus 20 would be 67, and which is not the best choice. So, this 53 that we had computed, it switches back to that. In practice, if I had not made that error of counting this as 57, it would have continued with that 53. Anyway, so now it is back to 53, and it follows this choice. There is only one choice below that, so it has to follow that, and between these two nodes, let us say it picks this node 4 for refinement. So, it has refined that node 4. So, this was a node it has picked for refinement, and it has one child, let us say, which has a cost 0, and so from 4 this has gone up to 10 essentially. It was 4 before this, it has gone up to 10. So, this is 10 plus 3 13 plus 20 is 33, and 33 and 6 is 39 plus 20 is 59. So, this still remains the best choice here, and then this is the node that we are refining next essentially. So, let us say that node also has the same child, which is this one here, and because it has a cost 0, the leaf node has a cost 0, but this cost goes up from 3 to 10, and so now it is 20 plus 20, which is 40, 40 and 6 is 66, and it is marked as the best choice. So, what was the other side? The other choice was, as you can see, 67, which is still little higher than the 66. So, 66 is marked as the best choice, and so we follow the marked choices. All this part of the solution is solved. So, there is nothing more needs to be done, only this part needs to be refined. So, this is what it does next. So, the thing that you would notice that when it is underestimating, it is oscillating between different options and is saying, oh, maybe that is a better option, maybe that is a better option. That is because each of them are being underestimated, as opposed to overestimating, which once it goes in some direction, it continues to think that that is the best direction. So, that is a node that we refined. This node had a value of 6. Now, it has got some options here. One is an AND arc with a value of 6 plus 8, which is 14 plus 20 would be 34, but this is a simpler choice. It has a cost of 0, and therefore, its cost has gone up a little bit. It was 6 to start with, it has come down to gone up by a little bit by 10, but because it has gone up to 10. So, 10 plus 40 is 50. So, this has gone up to 70. The other choice from this side was 69, and therefore, the arrow has switched back to the right hand option, which means it will follow the path. If you remember, the algorithm says follow the path, follow the markers, and it takes you to only one node that is left. So, you go and refine that, and when we refine that node, we get so this is a node that we are refining, and it takes you to a node with cost 0. So, it was 9, it has gone up by 1 to 10, and it has become solved. So, all this solved label keeps propagating upwards, as you can see. This is solved, this is solved, this is also solved, and therefore, the root is labeled solved with a cost of 70. The important point is that underestimation forces an algorithm to explore all options before terminating, and by the time it has finished exploring all options, it would have picked the best solution. So, this is just an informal argument we are giving for the fact that this algorithm AO star is admissible, provided the heuristic function underestimates the actual cost. Okay, next we will take a quick look at logic and deduction, and this process of goal directed reasoning, which is called backward chaining in logic, and we will see its connection with AND OR trees. We do not have time to do more in logic in this course, but the objective of doing this now is to tie it up with, say, the deduction in logic is also done via a process of search. It can be done either by forward chaining, which means going from the start state, which in the case of logic is the given knowledge base, to the goal node, which means what do you want to prove, or as we will see here, you can go from the goal node towards the start state. There is a third alternative, which is called the resolution refutation method, but we do not have time to look at that. So, when we come back, we will look at deduction with backward chaining and see its connection with AND OR graphs.